we're going to talk about the area between curves. So up until this point, when we're finding areas using definite integrals, we've been finding the area between a curve and the x-axis. In fact, we've been finding, when we're finding that area, we have a positive area if it's above the x-axis and a negative area if it's below the x-axis. In general, when we're talking about area, though, we want the area to be positive. So we're going to have to think about that maybe in a few cases here, where if we want to talk about the area or the definite integral, and there might be a difference there. So here's an example that I want to start with. I want to find the area between f of x equals sine of x and g of x equals cosine of x. They're graphed there. Sine of x is in green, cosine of x is in blue, on the interval from pi over 4 to 5 pi over 4. I chose nice clean numbers here. That pi over 4 and the 5 pi over 4 are the places where sine and cosine intersect. So there's pi over 4 right there, and there's 5 pi over 4 right there. And I wanted to make it nice and easy. So what we want to do here is find this area. That's our goal. With what we know right now, what are some options that we have here? Let's think about what the definite integral is approximating. Actually, the definite integral is not approximating, but let's think about how we approximated the definite integral. I should have said that in a different way. I'm just going to take a generic function here, and let's say I take the definite integral from a to b. How did I approximate this area right here? What did I do? What did we do first? So what we did is we made a bunch of rectangles, and we did what's called a Riemann sum. And a Riemann sum is a way of making a bunch of rectangles in here. And I'm just going to kind of approximate a picture here. Put in a bunch of rectangles in here and adding up the areas of each of those rectangles to get the total area, right? So and then what we did is we made those rectangles as small as we could. In fact, we made them the width of the differential dx, and it turned into an integral. So it went from the Riemann sum, using the sigma notation, to the integral. Well, we can do the same thing over here. We can break this up into a bunch of rectangles, but now the top and the bottom of the rectangle are not necessarily, neither of them is on the x-axis anymore. So the top of the rectangle is here on sine, and the bottom of the rectangle here is on cosine. Now let me ask this. On this interval, is there any place where sine is not above cosine? No. Sine is, on this entire interval, sine is above cosine. So what I can do to kind of picture what's going on here is I'm going to draw what's called a Riemann sum rectangle. So this is just one small rectangle that I would use to approximate this area. And I'll notice here that if I wanted to find the height of this rectangle, what would I do? What's that? Okay. So we would plug the x-coordinate, whatever this is here, we'll call this, say, point K. I don't like that. Let's use A here. I don't really like that either. Let's use C. I like that. Okay, so let's say the x value there is C. So if I wanted to find the height of that, Alex said we should plug it into sine and cosine and then do what with it? Subtract. So which one would go on top?
Sine.
Yeah, so we would take the sine of C minus the cosine of C, and that would give us the height of the rectangle. What's the width of the rectangle? You guys remember what we use for the width of the rectangles? How about delta x? Right? You guys remember that? Okay, so that's just the area of that rectangle. But if we add up all of these rectangles here, we're always going to do sine minus cosine. So if I want to change this notation here, this rectangle, and add up all these rectangles using an integral, what would that integral look like? What do you think? It's going to be the sine of x minus the cosine of x with respect to x. Remember that dx here turns into the differential x when we make those rectangles infinitesimally small. And we need to add up the rectangles all the way from where to where? Pi over 4 to 5 pi over 4. And there you have it. That integral right there is going to tell you the area between sine and cosine on that integral. Now this only works because why? Why is it sine minus cosine and not the other way around, Cole?
Because sine's always above cosine.
Yeah, sine's always above cosine. So since sine is always bigger than, or at least equal to, it's equal to cosine on the endpoints. But since it's always at least as big as cosine, then we can do sine minus cosine. If cosine were bigger, then we would do cosine minus sine. If we wanted to do something like from 0 to pi over 2, we would have to do two separate ones. We would have to do one where we do cosine minus sine over here, and one where we do sine minus cosine over here. So we would have to break that up. As far as evaluating this, we can use a calculator. In fact, I'd like you to practice using the calculator right now. So do me a favor real quick and evaluate this definite integral on your calculator. It turns out here that we're going to have square root of 2 over 2 involved here, so we're not going to get a rational number. Since we're using the calculator to do it, we're going to round to how many decimal places? 3. So what do we get? 2.828. And that's going to be your answer. I think it ends up being 2 square root of 2 if you're getting an exact answer. But like I said, if you're using a calculator, you're going around to 3 decimal places. We're using a theorem here that looks like this. We could call this the area between curves theorem if you'd like. So it says that if f of x is greater than or equal to g of x on the interval from a to b, and both functions are continuous, and that continuity was important even before when we were finding the area with the definite integral. You have to have a continuous function, otherwise the second fundamental theorem of calculus does not necessarily work. So if it is continuous, f is bigger than g on the interval, then the area between those two curves is given by this. If you have a case where g is bigger than f, then you flip it. You always do the top function minus the bottom function.